I'm very pleased to be here. It's my first Boyet conference. So they told me to discuss about datation and radiochronology. So in fact, I'm a geologist and I have started to use geochemistry during my master project and my PhD. I'm mostly interested about the early Earth formation and the early Earth differentiation. So I'm going to talk about the different systematics we can use to date very old events or very old samples. And because it's difficult to work on very old samples, because we have not much to study, I realized that we have also to combine measurement of terrestrial samples with the measurement of meteorites. So I'm a geocosmochemist. In fact, we can have information, but this is not absolute datation, but we can have information using the stratigraphy. So the stratigraphy is a discipline of the earth sciences that study the arrangement in space and time of the different geological formation. So for example, here you have a log. So this is typical what you can draw when you are on the field. So you start to identify the different rocks types and the different layers, and you have information about the relative chronology. Of course, you can understand that this layer will be older than this one, because on the top you have like younger samples. So the main goal of that is to reconstruct the history of the Earth and its evolution through time. We have also important information using the biostratigraphy. So the biostratigraphy is a branch of the stratigraphy which focuses on correlating and assigning relative ages of rock strata by using the fossil assemblage. So it's what is shown here. So we can see that you have different fossils in the different layers, and we have to understand that this is an irreversible succession of biological evolution, and this is the same. You obtain fundamental information about the chronology. The chronology, and because we can use the fossil, for example, here you have like the trilobite, we know that this is typical of very old fossil, so we have information on the age of this different formation. So today we have this geological time scale. So we are here now in the Holocene, and you go back to time to finish here in this period, the ADN. So in fact, this chart is an evolving chart. We have an international commission that look at the different results of the research, because you can see that it's combined information both using relative and absolute chronology. So for example, if one publication publishes a more precise datation, it's going to change a little bit to integrate this new result. And it's important to note that here we have like a column with absolute age, and this is obtained using datation and using radioactivity. So I just would like to draw your attention. You can see that when you are going back to time, so here I'm in the Archean and in the ADN, you can see that we have a long period. Here the ADN is 500 million years, and we have not many ages. It's completely different if you look at this period, because in fact we have very few samples available to work on this period. And here's the T0 we are going to use, and Brigitte talked a little bit about that. It's the age of solar system formation, and this corresponds to the refractory inclusion in the primitive chondrite, so the CAIs. We saw one CAIs in the sample, so yesterday. It was Allende, I think. And it's the first mineral that condensates during the cooling of the solar nebula. So T0 is here, and we are going this way. And in fact, during this long period, because it's close to half of the life of the Earth, we have very few samples. So we are going to talk about radioactivity because we use radioactivity to obtain absolute age on samples. So we have different elements. The different elements are characterized by the mass number, so the different isotope, and the atomic number. So if you look this chart of nuclide, you can see here the proton number and in the x-axis the neutron number. So for the same neutron number you have one element, and when you look on the horizontal line like this, you have the different isotope for a same element. So for example here, the samarium, we have 7 isotopes, and the neodymium here we have also 7 isotopes. And when we use datation, so we consider a radioactive system, and for example here we have 2 radioactive systems, the 146 samarium that decay in 142 and the 147 that decay in 133. And also what we need is several isotopes because we are measuring isotopic ratio. So that means that it will be not possible to use the datation if we have no different isotope for the measurement. So in fact, we have different kinds of radioactivity. I'm not going to talk much about that today, but what is important for us is to see this disintegration. So we start with the parent isotopes, and we have a disintegration to a daughter isotopes. We are talking about the radioactive, so the parent isotope, and the daughter isotope, which is radiogenic. So this is what you produce during the disintegration, and of course, for example here, you emit an alpha particles. So the basic principle of the radioactivity is described by this equation. So the number of nuclei that disintegrate per unit time is a constant fraction of the number of nuclei present. So we have 2 important information here, P, the number of nuclei, and here, the decay constant. And it's really important to note that the different systematics will have different decay constant. So if I integrate this equation, I have this one. So in fact, what you see is that the number of radioactive nuclei remaining, so this is the decay by time, it's a constant fraction of the initial abundance, and here you have the T, so it's dependent of the time. So in general, we do not use the decay constant, but in fact we use the half-life because it's more easy to understand. And the half-life of the radioactive element corresponds to the time it takes for half of the radioactive isotope to disintegrate. So in fact, it's just this quantity, and in general, when you see on the paper, it's this T that corresponds to the half-life of the system. It's more easy to understand when we look at the decay curve. So you start at T0, that means the closure of the isotope systematics with, for example, a constant abundance of the parent isotope, so here at P0. After one half-life, you have half of the initial quantity, so this is the half-life, 1T, and you can see that you decay with time, and after 5T, so 5 half-life, we have only 3% of the initial abundance of the systematics. That means that the system is extinct, that the system is closed. And this is important because we have 2 types of systematics, the long-life systematics, so the decay is still alive today, and the short-life systematics where the parent isotopes are extinct because the half-life is very short. So if we look at the different isotopes, in fact we have 3 different isotopes. The stable isotope, so the abundance is constant to time. So you start with this quantity and today you have the same quantity, it's stable, or the half-life is extremely long. We have the long-life radioactive systems that means that you start here and today the parent isotope is still alive. You can measure the quantity of parent isotopes. And we have the short-lived or extant radioactive isotope systematics. And here you can see that, in fact, the system is extinct because the short life is, the decay constant is very short. So today it's not possible to measure the abundance of parent isotopes. There is no more parent isotope present in the system. We have different long-life chronometers. So here you have a list that can be used. I'm going to talk much about the samarium, neodymium, and lutetium hafnium. Why? And also the uranium lead. Why? Because they are more robust to use for very old samples, because in general this work have a known different high metamorphic event, high temperature metamorphic event, and the closure temperature is high. So here the half-life is very long, and you have the description for the 147 samarium that decay in 143 neodymium, and it's the same for the lutetium hafnium systematics. So here you can see the half-life, so 100 billion years, 35 billion years, so the Earth is 4.5 billion years, so okay, the system is still alive. This chronometer will give you absolute age. You obtain an absolute age using this chronometer. But if we work with the extant radioactivity, so the short-life chronometer, I give you here one example. So that means that the half-life is short, and what is very good is that this short-life chronometer provides high-resolution information on the early solar system history, but you do not obtain an absolute age, you obtain a timing interval. And I'm going to give more detail about this different information you can have. Here you have the long-life systematics, so for example the rubidium strontium. So you are going to start here at T0, so this is the closure of your systematics. With time you have the decay of the parent isotope, so here in blue, okay, so the quantity decreases with time. And when you have the decay, that means that the blue, you lose a blue element to form a red element, okay? So with time, you decrease the number of blue elements and you increase the number of red elements. So in fact, you obtain this equation. So it's just here the production of radiogenic element to time. But what you see is that you have this equation, and with this equation we have two unknowns. Because what you are measuring today is this quantity. And this quantity is the sum of what you have in your system at the beginning and what is produced by radioactivity. But you don't know when you make the measurement if it was present before or just induced by radioactivity. So in fact, we have two different unknowns. It's this quantity and T. What I want to do is to date the samples. So I have two unknowns. And in fact, to resolve these two unknowns, we are going to use this method, which is called the isochron method. So here it's the quantity of isotopes, so the quantity of atoms. So I can consider that I have a work sample with three different mineral phases. One is called P, Q, and R. So these three different mineral phases have different affinity for the different elements. We call that the partition coefficient. So you can see that this mineral, okay, like a lot the rubidium, but in fact doesn't like too much the strontium. So it has a large quantity of rubidium, but not much of strontium. This one like a lot the strontium, but not much the rubidium, and this one is very poor for both elements. So this is at T0 when my systematic close. From this point, you start the disintegration. Because in this mineral you have a lot of radioactive elements, you are going to produce a large quantity of daughter elements. Okay? So in fact, this line, so this vector, the length of the vector is dependent of the initial quantity of parent isotopes. For this one, it's a little bit much than this one because you have a higher quantity. And for this one, you can see that the disintegration is very small because there is not much radioactive element in the system. But in fact, we are not going to determine the quantity of these different isotopes. What we measure is, in fact, isotopic ratio. Why we cannot do that? Because, in fact, the quantity is dependent of the mass of the sample. Okay? If you dissolve 1 gram, 2 grams, half a gram, it will be dependent of the mass of the samples. We don't not be dependent of the mass of the sample because it's extremely difficult to measure the mass with a very high precision. So in fact, what we measure is an isotopic ratio. So in fact, here you have to normalize using a stable isotope of this strontium. So in fact, if you do that, here it's exactly the same diagram, but I'm in isotopic ratio. All these minerals are in the same line. Okay? And through time, because this one has a lot of parent isotope, it will evolve like this one like this, and this one like this. And you can see that you have a new line, and this slope will give you the age of your samples. So in fact, if your sample is extremely young, you will have a slope like this, and through time, we'll have a steeper slope. So this is an isochrone plot. What I want to do today is to measure different, for example, mineral fraction or different rock sample, for example, coming from the same lava flow. And I will obtain an isochrone, and I have these two information. The initial isotopic composition, I'm not going to talk much about that, but I know that Eva will talk about that today. But I'm going to talk much about the slope. The slope gives you the age, because the age here, it will be a constant and it's dependent of the decay. Okay? So once you have the slope, you have the age of the samples. What is important to note is that if you want to have a high resolution age, you need to define the slope. If you have 3 minerals that are here, you will have a very big uncertainty on the slope. So it's important to find different minerals that have large fractionation between here the parent and the daughter element. Okay? And sometimes it's extremely difficult. So another systematic that is very interesting in earth science, and not only in earth science, is to use the uranium-lead geochronology. So in fact, it's powerful. Why? Because in fact, we have two decay of uranium in lead and even one more of thorium given an isotope of lead. So we have 3 different isotopes, systematics. And if I want to use this uranium-lead geochronology, I can consider only the 2 first one, because we have the same element, uranium and lead. I will have 2 equations, and I can construct, like Brigitte showed yesterday, this Concordia diagram. So why is it so powerful to use the zircon? For several reasons, because in fact this mineral is commonly found in crustal samples. Okay, so we can find this mineral in crustal samples, and these elements, these minerals are heavy and highly resistant at Earth's surface. That means that many zircon are transported, deposited, and preserved as detricate zircon. in sedimentary rock. So I can find very old zircon today, for example, in a river, and they have not been much altered during the erosion. In fact, if I consider these two different systematics, I can draw this Concordia, okay? And this Concordia curve, if I have a concordant data, that means that this age is consistent and therefore should plot on this Concordia curve. So here I show you one result. So it's a colleague in Clermont. He worked on Acastagnes, so they are extremely old, close to 4 billion years. And in fact, for this sample, what he did, it's in situ measurement. So he obtained, in fact, he drew a line using the laser and the ICP-MS, and he can determine the age of the zircon. Okay? So here you can see that you have a perfect Concordia age with a very good precision because it's only 20 million years. So we are close to here. But in fact, it's not always the case. Sometimes we have discordant data, and it's what is shown here. Okay? You are not on the Concordia, but in fact, we are on a line here. But when you are able to obtain this line, you have two information. Here, the upper intercept gives you the age of crystallization, and the lower intercept gives you the age of the open systematics. I mean, a secondary disturbance. Okay? So it's not the same sample, but it's a zircon, and in fact, he obtained different age on the same mineral. Okay? So all these age are obtained on the same mineral, and what you can see here is that he has a very nice information because he can define two different events. The age of crystallization using this upper intercept. The last systematic I would like to explain is the extent radioactivity. So it's close to this picture, but in fact what you can see is that the system is extinct rapidly because the parent isotope have a very short half-life. So that means that with time, you can see here, the systematic is closed. Okay? So today, I'm not able to measure a quantity of parent isotope because there is no more parent isotope in my systematics. So I'm only measuring the daughter isotopes. So if I try to look at this isochrone, I explain you for the long life systematics. Okay? So this is the long life systematics for the samarium neodymium, and this is the short life systematics for the samarium neodymium. So here I can measure the quantity of parent isotope and the quantity of radiogenic isotope because I have both in my system. And if I define a slope, the slope gives me an absolute age. Okay, I obtain an absolute age. It's not the same for short life systematics. So in fact, I'm only able to measure the quantity of the radiogenic isotopes, and here I cannot plot the parent isotope, so I'm going to plot on my isochrone diagram a ratio of two stable isotopes. It's just to show the chemical fractionation between my different minerals. So it's close to, it's the same information, but I'm not using the same isotopes. Okay? And in fact, we have the same information, but you obtain a fossil isochrone, and this fossil isochrone do not give you an age. This fossil isochrone will give you the quantity of the parent isotope when the system is closed. So it's not exactly the same information. Here you have an absolute age. Here you obtain the quantity of parent isotope when the systematic is closed. And it's the same. The steeper the slope, the earlier the planetary body formed or the event in question took place. Okay, so if it's old, you have a steep slope, and if it's not old, you have like an horizontal line. It's what we can try to do here. So in fact, this is just the decay curve for this isotope. So it's a short life isotope. So the half-life is 100 million years. So 100 million years after the beginning, you have half of the quantity of the initial abundance of the parent isotopes. And if I can obtain an isochrone, it will give me this ratio. And for example, if I find a ratio of 0.002, I will plot this sample on this line and I will obtain an age. But in fact, it's not an absolute age. It's an interval of time relative to my initial abundance. Okay? And this has been measured in CAIs. So the CAIs is the oldest mineral, or the oldest refractory inclusion we have, and we measure the initial quantity and CAIs, and after I can use this decay curve to propose different timing intervals. So in fact, we have a lot of different short-life systematics that can be used. So here it's the parent isotope, you have the daughter isotope, and here the half-life. So for some of them, the half-life is very short, 0.7 million years. So this one is mainly used to date very old objects on meteorites, for example. And if we want to understand the early fractionation on Earth, it will be not possible to use this one because it extends too early. But in fact, we have two nice chronometers, so the samarium neodymium, because you can see here that the half-life is 100 million years. So after 5 half-lives, the system is closed. That means that you can cover this Hadean period. So even if we have no work from this period, if you use this systematics, you have the potential to have information on this period. And one systematics that is extremely interesting, and I'm going to give you more detail on this one, is the hafnium tungsten systematics with a half-life of 9 million years. And you can use it to constrain the fractionation between the first 50 million years, which is extremely interested to obtain age, for example, for the core formation on Earth, or also on differentiated parent body. So here, I'm coming back to this systematics. I show you that here you have the decay of the parent isotopes. Because you disintegrate, you are going to increase the radiogenic isotopes. So in fact, through time, you increase this ratio. You decrease this one and you increase this ratio. But at one time, for example here, if I have a melting event, a crystallization event, I'm going to change the samarium neodymium ratio in my system, and then I can change the production of radiogenic isotope, and you can see here, for example, it will be the mantle, and I will have an excess in 142 neodymium in this reservoir. And it's in measuring very small variation in 142 that I can try to discuss what happened during the Hadean. So in fact, it's extremely important because during this period, a lot of important events occurred. So of course, you have the condensation, you start the accretion with different collision. We have this metal-silicate differentiation, so the core formation on Earth, the giant impact forming the Moon. I will give more constraint on that later, and the late accretion. So all these events occurred very early, and it's difficult to obtain information if I'm not using the short-life systematics. I'm not going to present the different instruments or to measure the technique for the measurement, but in fact, just to say that there is two types of measurement. We can use in situ measurement. So here it's, for example, a paper of aluminium, magnesium datation by the Nancy group, so using the hand probe. And here, a zircon, so we measure in Clermont, and you can see that you have two different information here. We can measure, for example, the lutetium hafnium systematics, and also to obtain an age of the sample. So all these pictures show you in situ measurement. But sometimes, and I mostly use this technique, you dissolve your sample. You are going in the clean lab to, in fact, isolate the elements you want to measure. So you have a long period of chemistry before you can go and make the measurement using the multi-collector ICP-MS or the thermal ionization mass spectrometry. So just to show the paper that give this age of T0, the oldest age. So in fact, they obtain an age on refractory inclusion, so it's not this one. So the refractory inclusion are made of mineral rich in calcium and aluminium, so rich in elements that have very high condensation temperature. And here on this CAI, so they obtain an age, so using the uranium lead systematics, and you can see this age with a very good definition. So 4, 5, 6, 7.35, and you can see the precision is extremely good. I give you one example. In fact, when you look all the data we have on CAIs, we can have a small range of different age, and this needs to be more constrained. But this is the T0, so the age of the solar system. So the hafnium tungsten systematics, I'm going to explain a little bit more. So why this systematic is so important? In fact, you have two different elements. This one is the hafnium, is a lithophile element. So that means that if you take a chondrite, so a chondrite has not been differentiated, you have hafnium and tungsten in this parent body. But because these two elements have two different affinity, this one is lithophile and the daughter element is siderophile, so he loves the iron and is going to go into the core of the different parent body. So you start at this step with an undifferentiated primitive body, and with the differentiation, you can see that all the hafnium, all the parent isotope is going to go in the silicate pair part of the parent body. So the mantle, the crust, but you have no hafnium into the core, nothing. And the tungsten is mostly siderophile. It's not an highly siderophile element, but most of the tungsten is going into the core. You have still a small part in the silicate part. That means that if I try to look at the ratio to time, here you have the chondritic evolution. Here the quantity increase because you have the decay of the parent isotopes. So with time, you are going to increase the quantity of radiogenic isotopes. So this is the chondritic evolution. We are here. But once you form the core, you have no parent isotope into the core. That means that you are not going to produce radioactive element. So here you stop and you have a constant ratio since, for example, 4.5 billion years to today. It's the same ratio. You are not going to change this ratio. And for the mantle, it's a little bit different because you increase the hafnium-tungsten ratio, you have more parent isotopes, so you are going to produce more radiogenic isotopes. So you can see that here you have more production, and today we have an excess in 182 tungsten relative to chondrite. Okay, so the different reservoirs are formed, the mantle and the core. And if I measure variation in 182 tungsten today, I know that I had differentiation occurring very early because 50 million years after the beginning of solar system formation, this systematic is extinct. So if I measure something now, that means that I see something that occurred at the beginning of solar system history. And in fact, this systematic has been really powerful to date the age of core formation, so on small planetary body, but also for the Earth. So this is a plot that we can that express the measurement in different meteorites. So it's not the isotopic ratio. So here it was an isotopic ratio. Here we express in epsilon. It's just to use like reference, okay? But it's the same information. So in fact, here 0 will be the Earth. Okay, my reference is the Earth. So my reference is the Earth. We can see that the chondrites have a negative value, so they have a deficit in 182 tungsten. And if we take the magmatic iron, we have a very large deficit in tungsten. So it's exactly this configuration. Okay, I'm measuring today. So the isotopic ratio for core, for iron meteorite, is lower than for the mantle or for the chondrite. Okay, so today I can measure different ratio. And in fact, I can use this isotopic composition to propose an age. So this is a relative age, an age relative to T0, so to CAIs. And we can show that the iron meteorites are extremely old. So I think that this is an old paper. Maybe today it will be more between 0 and 1. But the iron meteorite and the core formation on small planetary body formed very early during the first million years after the beginning of accretion. So now if I try to understand the isotopic composition we measure on terrestrial samples, so this is all the samples we can measure on Earth. It's not really true, in fact we have small variation. But I'm at 0, and we can see that the chondrites are close to -2. So I can use this difference to obtain an age of the mantle core differentiation on Earth. Okay, so this will be a model age. I have not a direct information, but I can obtain the age of the fractionation between hafnium and tungsten that is related to core formation. So, for sure, the Earth's core formation is formed very early during the lifetime of the 182 hafnium because we measure variation today. So you can remember this timing. So it's proposed between 30 and 50 million years after the beginning of accretion. So it's short, but in fact it's long when you compare to iron meteorite. It was 1, and now we had 30 or 50 million years. So maybe just for you to give you idea about the chronology. So here it's always datation using the aluminum magnesium systematics. And in fact, what they try to represent is so the information measured in different meteorites that are considered as the first planetary crust. So yesterday we see, for example, one eucrite, but we have different type of meteorite. And this gives you an idea of the timing. So this is a conversion of the parent isotope with age. So you have the CAIs, and in fact you can see that all these crusts form very early, between 2.5 and 5 million years. So it's the same. We can have very powerful information on the differentiation of the small planetary bodies, and they differentiated very fast, in fact, after the beginning of accretion. So one new information, so this sample has been found recently. So it's Erkshech 002, and it's a stone of 30 kilograms, so found in Algeria. And in fact, it's nice because this sample, it's an andesite bulk composition. So it's not basalt. It will be closer to the composition of the continental crust. If you take the continental crust today, it's an andesitic composition. And in fact, they measure that this lava is the oldest known lava that we measure. So in the collection we have in the different collection for the meteorite. So in fact, two papers. The first paper published by Barra last year, where he measures several plagioclasts using the in situ technique, and he finds an age of 2.2 million years. So recently we did new measurements, so using the MC ICP-MS, and in fact it was after separation of the different minerals. So it's not in situ technique, but you have to separate the different minerals, you go into the lab, you make the chemistry, and after you make the measurement. And we define a line that is close to 1.8. So the difference can be explained, in fact, if you have diffusion in plagioclase, which is possible. So sometimes it's better to analyze larger grain because you remove this effect of diffusion. So this is the difference. So here it gives you the age of crystallization of the samples. But in fact, we can have a second information. It's the first melting event, and not the age of crystallization, but the age of the melting event. And in fact, we obtain 1 million years. So we are close to the age we have for the iron meteorite. So we know today that the differentiation is extremely fast, in fact, and is close to the age we have for the CAIs. I'm going to move on Earth and to discuss a little bit about different formation and to show you the different information or debate we can have. So here you have the location of the very old sample we know. So of course the oldest one, but it's not a belt, it's only different minerals. It's close to 4.4, so here in Australia with Jack Hills. And after we have several important belts with age between 3.8 and 4 billion years. So the Aka-Stagnes at 4 billion years, Isua, so the Itzhak complex at 3.8 billion years. And the Sagleg complex. So we are always located in this part. If we look at South Africa, it's a little bit younger, so 3.6 billion years. And we have also a sample in China close to 3.8 billion years. But you agree that we are always in this location, but there is nothing, no samples with very old age except the Jack Hills zircon. So the Jack Hills zircon, I give you the result for two different papers. So the first paper with an age of 4.4 billion years, just to show. So maybe it's too small, but in fact you have different age in the same mineral. Okay, so because they are in situ measurements, and in fact you have only one spot at 4.4. So that gives you an idea of the complexity of the measurement, because in fact you can have several phases of crystallization for the same minerals. And so here you have only one age at 4.4. They decide to take another zircon close to 4.4, and this is a new technique. And in fact, they redefine this, this zircon at 4.37 million years. So we are close to 4.4 billion years. But it's not 4.5 billion years, okay? It's younger than the beginning of solar system formation. So this is for jack hills. So they are detrital zircon. So you have zircon in sedimentary rocks, okay? We have no information of the initial rock, it's only zircon. And in Acasta, okay, Acasta gneiss, we have a zircon here, but in fact, only the core of the zircon has an age of 4.2, but all the age are close to 4 billion years. So it's using this sample that the limit between the Hadean, we have no sample, and the Archean has been defined. 4 billion years, because we have sample at 4 billion years in Acasta. In fact, if we look at the diversity of zircon we have in Australia, so this is a publication where they try to, so it's an automated technique, so they try to define the age in a large quantity of zircon. So here you can see all the zircon that they measured, and of course, so I'm not going to see much the scale. So yeah, in fact, when you can see here, it's extremely difficult to find very old zircon. So in fact, they take a lot of rock, they crush the rock, they separate the zircon, they mount the different zircon, and after they make the measurement. And here it's just a zoom on this part. And it's the same. You can see that it's extremely hard to find very old zircon. So yeah, we have evidence for a crust of 4.4, but we have a very few zircon showing this information. I'm going to speak a little bit about the Nouveau Agituk Western Belt. So here you can see that on this slide I have two ages reported, 4.3 and 3.6 billion years, because it's difficult to obtain an age for this formation. What I told you before is that, okay, it's very easy if you have zircon, but zircon is present in continental crust. And the first crust on Earth was not a continental crust. The continental crust, you need to have like two-step processes. So the first crust should be more mafic, closer to what we call the oceanic crust. And you have no zircon. So it's not possible to obtain age for this formation because you have no zircon. This is why there is all this debate on the Nouveau Agituk belt. It's in fact because if you try to obtain an age of zircon, you can find zircon in several units, but they are not extremely, but they are young. Here you are 3.4, 3.8, and there is no zircon in this part of the belt, which is more mafic in composition. There is no zircon. Jonathan O'Neill worked a lot on these samples, and he has two important information. First, one isochrone using the long life systematics, and he has an age of 4.1 billion years. So it shows that it can be older than Acasta. And if we measure the short life systematics, but the short life systematics does not give you an absolute age, he obtained this age, so it's close to 4.3 billion years. So we have two different information here. This should be the minimum age, but this is a huge debate in the community. Some people say that no, it's not an isochrone, we cannot consider this age. But if we believe this isochrone, that means that in this part of the world, you have the oldest piece of the crustal section found on Earth, which is close to the age of the zircon we have in the Jack-Hills formation. So now the information we obtained on Isua. So I work a lot on Isua, on Greenland, because it was the subject of my PhD. So in fact, we have a small belt. It's not really big. You can see the scale. It's 2 kilometers. But we have very interesting rocks. For example, you can see these pillow lavas. So that show you like lavas deposit in ocean. And in fact, of course, because they are very old samples, they have known different tectonothermal events, so during the early Archean, late Archean, and mid-Proterozoic. But we can still have important information, and we can measure the age of these samples. So here it's just to show you two different results. We try to obtain information using two long-life systematics, so the Samarium neodymium and the Lutetium hafnium systematics. And we measure a large quantity of samples because we were interested to obtain the more pristine samples to after measure the short-life systematics on these samples. And what you can show here, it's for the long-life Samarium systematics. In fact, I have two different isochrones, okay? It's not really isochrone. I have two slopes. So the first one with this green sample gives me the age of the crystallization, 3.7 billion years. But you can see that for this sample, the systematic has been opened. It's not an information on age of crystallization, but in fact, it gives you an information of the metamorphic event. So if you want to characterize the metamorphic event, it's good. But if you want to date this age or to obtain information on the source, you have to focus on these samples. And in fact, these ones are extremely poor in neodymium, so it's more easy to open the system. And if we take the same sample for the Lutetium hafnium systematics, they plot on a nice isochrone. We obtain an age that is the same, so 3.7 billion years. But you can see that several samples are not on this isochrone. So yeah, sometimes the systematic has been open. And when you are on the field, you select your sample. You don't know which one is open or is closed. So you have to make all these measurements before to select the good sample to measure the isotopic composition, for example, in 142 neodymium. So this is the first step. And sometimes the Lutetium hafnium system is more robust to post and placement modification, but not always. I measure samples in different contexts, and sometimes it's the Samarium neodymium that is closed and the Lutetium hafnium that is open. So if we try to measure the short-life systematics in the same samples, so here it's the Isua samples, so from different units, you can see that most of these samples have excess in 142 neodymium. So the value here at 0, it's all the modern terrestrial samples. But if I go back in Isua, I have excess in 142 neodymium. And that's exactly what I try to explain to you. If I measure an excess in 142 neodymium, that means that an event, a melting event, occurred during the ADN. So even if these samples are 3.7 billion years, I can use this information to find the event of fractionation before, so in the source of these samples. And in fact, using these two systematics, we can obtain the information on the fractionation because I have two systematics, the long life and the short life systematic. So I take all these different information, I can combine this different information to define the age. I obtain plot like this one. Okay, so this is the deviation in short life systematic, the 142, and this is the parent-daughter ratio, so obtained from the long life systematics. And if you do that, you can see that all the samples, the terrestrial samples, so the very old terrestrial samples coming from different locations, Acasta, Isua, form an isochrone. This isochrone gives you an age of 4.4 billion years. So we think that a major event occurred on Earth at 4.4 million years, and this is probably related to a magma ocean stage just after the giant impact. So we are very close to the age we measure for the zircon, 4.36. So in fact, it seems that we have no information before because this major event was late, in fact, is not very early in the solar system history, but more close to 4.4 billion years. So I'm going back to the moon because in fact it's probably related to the formation of the moon. So we think today that the last magma ocean stage on Earth was caused by the giant impact forming the moon because we have similar age for all these different objects. So just to go back to the magma ocean stage, so this is a lunar concept and in fact it's old, it comes from 1970 and Wood et al. Were the first to suggest that an anorthosic rocks, so this type of rocks, could be the remnant of the earliest lunar crust formed by crystal fractionation and plagioclase flotation during the crystallization of the magma ocean. So that means that you have a moon that is molten, okay? And you are going to start the crystallization. So you crystallize from here to the top. You are going to start with the crystallization of olivine and pyroxene. They are dense, so they are going to go here at the lower part of the magma ocean. And when you continue the crystallization at one step, close to 70–80% of crystallization, you start to crystallize the plagioclase. But in fact, the plagioclase will float to form this thick anorthosic crust. Okay? Donc you are going to crystallize the crust and you have still a large part of the moon that is molten. And after that, you finish the crystallization with this creep. So here, this creep reservoir that is extremely enriched in incompatible elements because it's the last liquid to crystallize during the sequence of crystallization. We have this model for the moon. Of course, when you look at the moon, you can see that we have two different samples, very different samples. A large part of the moon is white, and they are the lunar island, this type of rocks, the ferroanorthosite. And you have here all this black area, it's the lunar maria. So this is the part of the moon we can see, but in fact, if we are going on the dark side of the moon, it's only lunar island ferroanorthosite. So we have samples coming from the moon with the Apollo mission. So I didn't report the different Apollo landing sites, but you can understand that it was more easy to land in this Maria because it's flat, and it's extremely difficult to land in this lunar island because it's really island and the topography is complicated. But we have one mission, Lunar 16, that was in this part, and we have samples from the lunar island coming from the mission Apollo 16. In fact, I'm not going to give you too much detail, but I think this is a nice plot. So it's the same. You are going to take information coming from the two systematics, the short-lived 146 samarium, 142 neodymium systematics, and the long-lived 147, 143 neodymium systematics. And in fact, if you do the same, I showed you before for the terrestrial samples, we can see that the slope is very close for the moon and for the Earth. Okay? So if I take all this age we obtain for the planetary isochrone, so using the short-life systematics, I'm close to between 4.4 and 4.3 billion years. And I have the same information if I take the model age coming from different long-life systematics, and I have exactly the same information if I try to obtain an absolute age, and I can do that if I date the crust of the moon, because we think that the crystallization of the magma ocean is extremely short. So if I can date the age of the crust, I can obtain the age of the magma ocean stage. And in fact, it's old now. 10 years ago, we worked on these samples. So it's an anorthosite, and in fact, we select this sample because he has this pyroxene. Okay, it's what I showed you before. If you want to date samples, you need a slope. And you can see that this slope is obtained because you have a pyroxene. Otherwise, it will be not possible because all the different minerals will be here and you cannot have a slope, okay? Because they have no fractionation between the parent-daughter, between the different elements. So we decide to work on this sample, and for the first time, in fact, we use 3 different systematics, the long-life systematics, the uranium-lead systematics, and also the short-life systematics. And it was the first time that 3 different systematics give a concordant age for the moon, for the anorthosite. So you can see here you have 4.35, 4.36. It's a little bit more complicated with the short-life systematics, but it's the same, it's 4.32 billion years. It's exactly what I show you here, and now there is different publication with the different, on different samples, and we have a very good agreement with all the different estimates to date the age of the moon. That means that here, if it's a giant impact, that explains why we have no record of the first 150 million years, because all this part of the terrestrial record has been lost due to the giant impact. I'm going to just to show you a last, I think it's a nice result, so I decide to show you this result. On this part, so on the oxygenation of the atmosphere, and how we can bring new constraints using the datation. So I'm sure you know more than me this figure. So what it shows is the quantity of oxygen in atmosphere, and in fact what you see is that during this first period of the Earth there is almost no oxygen in the atmosphere. And after you have this big event, so which is called the Great Oxidation Event, that is dated between 2.43 and 2.31 billion years, and you increase a lot the quantity of oxygen in the atmosphere. But in fact, what we think is that maybe there is some pulse of oxygenation before. It's not just one event, but in fact we have pulse before this great oxygenation event. What we decide is to work on the rare earth element. So in fact it's important because if you look at the rare earth element of the seawater today, we can see that you have this large anomaly in cerium. Why? Because the cerium has 2 valence states, cerium 3+ and cerium 4+, and under current oceanic condition, cerium is oxidized and is insoluble, so it will be subtracted from seawater. Okay? So in seawater today, you have this large fractionation between the cerium and the 2 neighboring rare earth elements. So in fact, this cerium anomaly has been studied to try to define this, because when you have no oxygen, there is no reason to have this fractionation. the cerium should be close to the lanthanum and to the praseodymium. In fact, what we decide is to apply this systematics because it's lanthanum cerium, so we can use this systematic to date a fractionation between these two elements. It's difficult because, in fact, it's a very, very long half-life, 300 billion years. That means that the radiogenic production is extremely small, and it's difficult to measure because we want to measure very small variation. But we try to apply these systematics, and for that we work, so it's a paper published 2 years ago. So we work with Stéphane Lalonde on banded iron formation, so BIF, coming from the Moody's group, so in the Barberton-Bristol belt, and this sample have been dated at 3.2 billion years. In fact, when you look at the rare earth element pattern, so I'm sorry it's a big mess because there is a lot of samples, but you can see that for a few samples we have this large cerium anomaly, okay? So we have this deficit in cerium relative to the two lanthanum and praseodymium elements. So we apply the systematics, and in fact what we measure is no difference in cerium isotopic composition. That means that if we try to construct the isochrone at 3.2 billion years, it's this slope. So it's clear that this cerium anomaly is not a primary signature in this sample, but in fact it has been probably caused by a secondary event that is very recent. And this is important because sometimes you can try to interpret proxies or signature, but in fact, if you have no time constraint, you don't know if it's a primary signature or if it has been caused by an event yesterday or a few million years before. So this was maybe not good to interpret this in terms of oxygenation, but in fact you say that, okay, it's very important maybe to combine the information coming from isotope systematics when you can date event to be sure that you interpret the data correctly. And I'm not going to give you more information, but we measure new samples that are extremely old, so 2.9 billion years, but it was a few weeks ago, and we have a nice isochrone at 2.9. So yeah, I agree with that. For some samples, we have large cerium anomaly coming very early and before the great oxygenation event. I'm going to stop, so thank you for your attention. Just a few words, but it's for the French community. Nous avons le colloque du PNP à Lyon du 29 juin au 1er juillet. Donc le PNP, c'est le Programme national de planétologie, avec différents thèmes. Hein. Le PNP, il est divisé en 4 thèmes, donc c'est assez large. Ça reste INSU, donc c'est astronomie, sciences de la Terre. Voilà, donc il y aura la communauté qui sera présente. Donc si jamais vous voulez venir à Lyon, donc ça sera à l'ENS. On va bientôt ouvrir le site pour la soumission d'abstract. Donc je vous encourage à venir découvrir la communauté française.